Hello everyone, this is lesson 4 of precipitation and solubility. So today we're going to be talking about precipitates and how we can use the KSP, the solubility quotient, to determine if a solution will precipitate with a certain concentration. So saturated solutions are the ones we talked about last time. These are solutions where the concentration of solute, that is the concentration of the dissolved ions in our case, is at the exact point where a precipitate would form if any additional solute was added. So it is a solution where the solute that dissolves with solute that dissolves until it is unable to dissolve anymore, leaving the undissolved substances at the bottom. That would be saturated. So the saturated solution cannot accept any more solute into solution. If we contrast that with the unsaturated solution, in the unsaturated solution, then we would find that the solution will still completely dissolve any solute because you're below that equilibrium point. So essentially you have no solid in equilibrium in an unsaturated solution because you still don't have enough. Thinking about our reaction quotient, we can think about, or let's think about the equilibrium because that still applies. You have some solid, right? And that solid is being broken apart. Let's call it AB just so we have something to deal with here. So we have a solid AB and it's separating into some sort of positive aqueous ion and some sort of negative aqueous ion. If these concentrations are very low, so very low, then the chemical equilibrium will be heavily shifted in this direction, right? We're going to have heavy shifting in that direction to compensate. So essentially, if the concentrations are very, very low for the two solutes in the unsaturated case, then this will essentially become zero. So there will be no solid. And so that's the idea. Now we can use the same idea as the reaction quotient, the Q, as a test of the equilibrium condition to see if you are at or below the KSP or above the KSP. So if we are able to determine the concentrations of a solution, of the ions in solution, we can then fulfill the this equation. In this case we have, the general form here, whatever. And we can fulfill this equation. And if this value for Q is exactly the same as KSP, then the solution is saturated. And there's no precipitate forming, or no more precipitate forming, no less precipitate forming. There's probably solid at the bottom, but that amount of solid is not changing based on the saturation. If Q is greater than KSP, then the solution is saturated and a precipitate forms. That is, not all of the solid will be able to dissolve in that solution. So if you are trying to make a solution and you calculate out the concentrations that you're mixing, it is most likely that if you are creating a solution that has this situation where the solution has a higher Q than KSP predicts, then that solution will have precipitate forming. And exactly. If Q is less than KSP, then the solution is unsaturated and no precipitate forms. Now there is one example here where you can do some trickery. If a solution is prepared at a higher temperature, then KSP is different at that temperature. This could allow higher concentrations And a concept called supersaturation can happen. So I'm going to just convert that. I realized that as I was writing it, this is getting kind of messy, so let's just see if we can fix this up a little bit. So remember that KSP, or K constants in equilibrium, are dependent on temperature. So if a solution was prepared at a higher temperature, the KSP would be different. At that temperature. This could allow for higher concentrations of ions, and when the solution is carefully cooled, they may remain in solution. This is a supersaturated solution. And a very cool concept, you know, sort of outside the scope of what we're talking about right now, but something that we discussed in our grade 11 course. Those supersaturated solutions, very cool, very fun to work with, but it's also very temperamental. With a supersaturated solution, if you disturb the solution, even something like putting a glass stir rod in, you will find that precipitate will immediately form because the concentrations are at a state that is above the KSP. So I just want to point that out because there are situations where you could create a solution that satisfies this Q being higher than KSP, but usually using temperature changes. Alright, so the KSP of lead 2 chloride is blah. If 0.57 grams of lead 2 chloride is added to 1500 mils of water, is the solution saturated? Assume no volume change. Okay, so we got a lot of stuff going on here. We have a lead 2 chloride, so that would be PbCl2. So it might be worth writing down a molar mass for this because we do notice a value in grams here. So I'm going to write some molar masses here. That's 207.2 grams per 1 mole. And we get to add that to 2 times chlorine, which is, I think it's like 35 point something. Just a second, I'm pulling up my calculator here. 35.4. 35.4 grams per 1 mole. Certainly if you do enough chemistry, there are going to be certain molecular weights that you just remember. I did a lot of work with lead, and so I tend to remember the atomic mass of lead, and actually did a little bit of chlorine stuff. 207.2 plus 2 times 35.4. So that is my molar mass. So there's 278 grams per 1 mole for lead chloride. And we have 0.57 grams of that stuff, and we're going to dissolve it in 1500 milliliters to give us a concentration. That's really what we really need. So we need that concentration of lead chloride. And so the way I think about that is that I am thinking about how I want to get to a situation where I have moles over 1 liter, right? And so to get to moles over 1 liter, I'm going to take that initial mass, I have to start with whatever they gave me. So they gave me 0.47 grams. So I'm going to multiply that by the inverse mass ratio. So that's going to put my 278 I just finished calculating down there. And that's going to give me moles. And then I want that moles over liters. And so I'm going to also multiply that by my volume, or I'm going to multiply it by a fraction of my 1500. And now is that milliliters? It is. Well, okay, why don't we do something like this? Just to be completely everything. And remember that there are 1,000 milliliters in 1 liter. And so going through this, I should see that the milliliters will cancel out, the grams will cancel out, and I will be left with moles over liters. Okay, so let's do some work here. 0.57 times 1 divided by 278 times 1 divided by 1500 times 1000 divided by 1, and that gives me my molarity, which is 0.001367. I'm going to keep a couple of extra significant figures because I'm not quite done with this yet. And I know I probably only have 2, maybe 3 significant figures to play with, but these were all constants so far, so I haven't really played around with. Oh, I guess I have 2. I have 2 significant figures from that 0.57, don't I? So at the end of my day, I'm going to have 0.57. Okay, so the KSP is this. So now this is just the concentration of lead chloride if all that lead chloride is able to be in solution. So I know that lead chloride breaks down into its composite parts, which is the lead 2 plus the chlorine minus. So lead chloride, the solid, will break down into this aqueous forms. And I'm going to get 2 of those actually. So whatever my concentration is here, this means that I'm going to get the same. This is going to be equal to the same concentration for lead, because that's a 1-to-1 ratio, 0.001367 molarity. But for my chlorines, it's a 2-to-1 ratio, so my chlorine is going to be twice that. 0.00274 molar. And then what else do I have to worry about? I do have to worry about one other thing, don't I? Oh, yeah, well, let's just do that Q calculation. So Q here is going to be equal to, because of this equation, Q is going to be equal to the concentration of lead times the concentration of chlorine raised to the power of 2. So let's do a little test calculation here. And see how we did. So Q is going to be equal to 0.001367 molar multiplied by just suddenly got the irrational fear that I made a mistake, and then students would be shouting at their screens going like, what are you doing? But oh well, can't live in the what ifs. Have to live in the now. Okay, so my result is a very small number, 0, and we did say it would be 2 significant figures, right? So I guess I'm going to get 1.0, and we're going to say times 10 to the negative 8. And let's check against our KSP. The KSP is 10 to the negative 5, so right now we can say that Q is less than KSP, so this means that there is no precipitate. Or it is a unsaturated solution. Right now, any additional solid you put in is going to be shifted to that right. So looking up here, I'm going to clean up a little bit. I think that should be up here. Let's put the little thought bubble on this one. If we look at our equation right here, then we can think of that these concentrations are so low that the equilibrium is shifting to the right as fast as it can, and it's actually using up all of the lead chloride. So effectively there's no lead chloride in the solution, or nearly, there's not enough that's visible, and so until we hit that equilibrium point, we are going to not see any solid floating around. So that is an unsaturated solution. Okay, let's try the second example. So a little bit more of the same, but a little bit different. Here we have some other things going on. So if 20 mils of this solution is mixed with 20 mils of this solution, does silver bromide precipitate? So they are discussing one of these precipitation reactions, right? AgNO3 plus, and they're saying it's aqueous, right? And they're going to add that to potassium bromide, which is aqueous. And they're hoping that a chemical reaction will happen, which will form silver bromide as a solid, plus any aqueous leftovers, in this case potassium nitrate. And so we would look at this, we could do a net ionic equation, so let's just do one of those. Net ionic. And the net ionic, we would cancel out the nitrate, cancel out, maybe I'm going to do a real shorthand here version of this. We got a nitrate on both sides that's aqueous, we got a potassium on both sides that's aqueous. So we are looking at a new equation that's just Ag plus aqueous plus Br minus aqueous, and that is giving us AgBr solid. So that's the reaction we're proposing. We know now that net ionic equations are okay, but we are going to use a flipped version and say, hey, you know what? These are actually equilibria. So let's draw out that equilibrium here in the proper orientation. So it's okay. So now what I'm looking for is I really want to know what are these concentrations, because I have a KSP equation that will tell me if there's a solid that's going to form, but for that KSP equation I need to know the concentrations of the silver and the bromide, and I guess technically I'm going to do a Q test first. So I'm going to do a Q check because I don't actually know if this is an equilibrium system, and so I'm going to do a quotient product. Okay, get there. Well, we have a concentration of silver nitrate, right? So we have a concentration here, 0.0010 moles per liter. And we have a concentration here of 3.0 times 10 to the negative 5 moles per liter. And then they were mixed together, and then there's going to be now this is going to imply something about these two and what the concentrations are here, right? This is what we're interested in. So let's do a little diagram, because sometimes I find that I need to think about what's actually going to happen here. So I've got here's my little beaker, and I'm going to have another beaker here. In this beaker, I have a volume, which is 20 mils, and I have this concentration. Let's just call this one this is going to be our silver nitrate. And we said that their concentration here was that 0.001. 0 molar, and I have a volume which is 20.0 milliliters. And on this other side I have 20.0 milliliters and is my volume, and I have that the very small concentration. What did we say it was? 3 times 10 to the negative 5. Okay, so these two solutions are being added together into a single reaction vessel, right? I'm going to make this one a Erlenmeyer flask just so I have a different shape to work with. And so the thing to think about is, what is the volume now? What is the concentration of silver? What is the concentration of bromine? Okay. So a very useful equation that we may not have covered, you haven't covered in a long time, or maybe not at all, is an equation that looks like this. Concentration 1 times a volume 1 is equal to a second concentration times a second volume. So this is an equation that's used for dilution. This is a dilution equation. Dilution equation. So assuming you start with some amount of some solution and you increase the volume to a second value, then you can rearrange this equation to figure out what the new concentration is. You can also use it to figure out how much you have to increase the volume by in order to determine a concentration. So for example, here, this is the concentration of silver nitrate, but it is also equal to the concentration of silver. Hopefully you agree with me. Silver nitrate dissociates into a single silver ion, so we can say that the concentration of Ag plus is, and let's call this one number 1, is equal to 0.0010 molar, and its initial volume, volume 1, is equal to 20.0 milliliters. When you add the two solutions together, the new volume is going to be 40 milliliters because you are adding two 20 milliliter solutions together. So this volume is going to be 40.0 milliliters. So now the question is, what is silver in that second volume? Maybe don't like how that looks. So let's try concentration 2 of silver. So let's set that up into this new dilution equation. We have 0.0010 molar. That is moles per liter, so we should probably convert our volume into moles into liters as well. And we say that is equal to concentration 2 times the volume of 0.0400. And please, please, please always convert everything, just because the one time you try to skip ahead a little bit, you're going to probably end up making a mistake, and you're going to be very sad when it comes back and you don't get the right number. Right, so I'm going to do some math. 0.001 times 0.02 divided by 0.04 equals my new concentration, which is 5 times 10 to the negative 3. So I got a 5 times 10 to the negative 3 molar solution of, which is my silver. It is the concentration of silver nitrate if you want to focus on that, and then we could separate out the ions later. It's also the concentration of the silver ions themselves. It's also equal. Let's call that number 2. It's also the silver nitrate if you want. Number 2, doesn't matter how you want to represent that so much. Okay, so let's take the 3.0 times 10 to the negative 5, which is our bromine. We're going to multiply that by the 0.0200 liter of bromine. This is equal to concentration 2 of our bromine, and that is times by the new volume, 0.0400 liters. Carry out the work here. I'm going to just copy all this, duplicate, place that there. Okay, so you're all just repeating yourself, and I haven't even started doing the Q equation yet. Okay, and in this case, we're actually just dividing by 2, aren't we? But that's okay. And it was 3 to the 5, right? So 3's 3, 1, 2, 3, 4, 5, yep. Okay, and so we end up with a final value of 1.5 times 10 to the negative 5 molar, and that is my new concentration of bromine, or of the KBr. Okay, so my Q test it's time for the Q test. I wrote that out up here way back. So I'm just going to take another copy down here so I can do my final steps here. Replace those values with my new values. So this is definitely like on the scale, one of the more tricky things that we are doing in this unit, largely because it incorporates a couple of long forgotten skills like the dilution piece here. And there is, of course, more math. Oh, this is not M. This is now just KSP. This is now Q. Okay, so now this is where we go and we look and find that KSP value. We see the KSP value here is much smaller than the silver bromide concentration we just calculated. So here we have Q is much larger than KSP, like 5 orders of magnitude. So precipitate forms. So this is the kind of question, this is the kind of reaction we would see a rapid formation of precipitate at. And with that, that's the 2 practice questions. So go ahead and try some of these other practice questions, and we'll come back a little later with our next video on other stuff. Notice that we give you lots of room on the common ion effect, of course. All right, have a great day.